And our final speaker for today before the discussion section will be Marie Lau.
I hold this?
Clip it on your pocket. Do you have a pocket?
I don't have a pocket, but I can hold this.
Okay, that would be great.
Hi, can you hear me? Yeah, hi, I'm Marie Lau. I'm postdoc at UC Riverside. I'm very happy to be back to Santa Cruz. I'm presenting a work in collaboration with Fred Hammond, Jared Gillett, Serena Peralta, and also Rupke, Walezelek, Zakamska, and Vayner. I'll begin with introducing why you should care about dusty quasars and the extremely red quasar population. Then I'll describe our KCWI observations of Lyman alpha halos around ELQs. Then I'll talk about implications of our measurements on the inner circumgalactic medium, implications on the quasar illumination geometry, and putting it in the context of quasar and galaxy evolution. And I'll end with listing our ongoing work. The figure on the right is a part of that Hopkins figure, showing 3 intermediate stages in popular galaxy evolution models. The models predict that supermassive black holes initially grow in obscurity deep inside dusty galactic starbursts, and the supermassive black holes grow until blowouts of gas and dust quench star formation. Then the blowouts reveal visibly luminous quasars in the galactic nuclei. Dusty quasars are the middle stage here. They provide important tests of evolution models because they're expected to be young and powerful objects. They should appear during that brief blowout phase that is a transition between the initial dusty starbursts and the later normal blue quasars. Many dusty quasar populations have been selected using a range of color and brightness criteria. For example, the hot dust-obscured galaxies, hot dogs. Many of these populations require more powerful physical properties than what could be just AGN orientation effects. Further, dusty quasars are the dominant population of the first quasars, so they're really unique laboratories. The Hammond et al. Team discovered a unique population of dusty quasars that we named extremely red quasars. ELQs are selected from the BOSS survey matched to WISE data. They're selected based on extremely red colors from direct UV to the mid-infrared. ELQs are at redshifts 2 to 4 and have high intrinsic bolometric luminosities greater than 10 to the 47 ergs per second. Relative to other dusty quasar populations, ELQs are more uniformly selected and well-defined, and they have more exotic spectral properties. The example illustrated here is the reddest of all ELQs. The figure on the left shows the central 1 arcsecond spectrum extracted from KCWI data of the reddest ELQ. The vertical lines mark locations of prominent emission lines in the systemic frame defined by that Lyman alpha spike at 2.3184 redshift. The systemic redshift reveals that the blue shifts of the broad emission lines are very large. And these unusually strong broad emission lines also have peculiar wingless profiles. The most notable spectral property of ELQs is their O3 emission. This figure in the middle shows the rest optical spectrum of this ELQ. I overplot a Sloan composite type 1 quasar spectrum for comparison. ELQs drive the broadest and most blue-shifted O3 5007 emission ever reported. The O3 outflows can carry speeds reaching 6,000 kilometers per second. Because of the atomic physics, O3 emission traces gas on roughly 1 kpc scale, so the quasar feedback is reaching the host galaxy. In the rest UV spectra of ELQs, narrow Lyman alpha emission spikes are common. Narrow emissions have to originate from gas on scales much larger than the broadline region. So the spikes tell the ELQ should power Lyman alpha halos despite the obscuration. We observe their Lyman alpha halos for 2 goals. First, we measure the inner circumgalactic medium around them, which is accessible thanks to the obscuration. Second, we test the hypothesis that ELQs are in an evolutionary stage different from other quasars. ELQs are a well-defined sample. They are ideal targets. The fly likes me. They are ideal targets to advance Lyman alpha halo studies beyond random surveys or exotic single optics. They can advance Lyman alpha halo studies to test of the evolution paradigm that are both statistical and specific. A student and I observed a sample of 11 ELQs with KCWI. For each data cube, we extract a spectrum from a 1 arcsecond aperture centered on a quasar. Here I used the Reddest ELQ in a sample J0006 to illustrate the measurements, and the measurements generally apply to the whole sample. Dust partially obscures the broadline region, so narrow emission components in the central 1 arcsecond can be identified as kinematically distinct components. The narrow Lyman alpha, narrow carbon-4 1549, and narrow helium-2 1640 have very similar peak velocities and velocity widths. The spatially unresolved O3 emission also has a narrow component that has very similar peak velocity and velocity width. We construct the spatially unresolved quasar spectral template by subtracting the narrow emission from the central 1 arcsecond. And then we use this template to model the quasar point spread function. Then we optimally extract the extended line emission. We detect spatially resolved helium-2 and carbon-4 emissions with kinematics similar to the Lyman alpha halo. The figure on the left shows the extracted image of Lyman alpha. The plus sign marks the quasar, the cross marks the Lyman alpha halo's peak. The middle figure shows the extracted image of carbon-4, and the right figure is helium-2. For the Lyman alpha halo, we define a flux unweighted eccentricity parameter and a flux weighted eccentricity parameter. The unweighted eccentricity is sensitive to the overall halo morphology. The flux weighted eccentricity is sensitive to the inner halo morphology. A value of E much less than 1 would indicate very circular morphology, and a value of E close to 1 would indicate very asymmetric shape. And we calculate the carbon-4 to Lyman alpha and helium-2 to Lyman alpha line flux ratios where the lines are detected. We create a Lyman alpha line velocity centroid map. It's obtained as the first moments of the flux distribution and is shown on the left. There is usually not enough signal to calculate reliable second velocity moments. So for the Lyman alpha velocity dispersion map, we Voronoi bin the KCWI data and fit Gaussians to the Voronoi bin map. This map is shown in the middle. We define 3 apertures according to features on the velocity map and of the morphology. On the Lyman alpha velocity centroid map, we show a circle and a slanted line that delineate these apertures. We delineate an outer region and an inner region with a circle of radius 23 kpc. We further divide the outer halo following the transition in relative velocities. These aperture spectra are shown on the right. I also show the central 1 arcsecond spectrum for comparison. This vertical dashed line marks the blue shifted absorption trough in the inner halo spectrum. The peak velocity and velocity width of the inner halo is very similar to that in the Lyman alpha spike in the central 1 arcsecond. We have the advantage that quasar reddening acts as a coronagraph that allows views of the innermost halo. So we confirm that the Lyman alpha spike in the central 1 arcsecond, which is otherwise dominated by quasar emission, is inner halo emission. Narrow emission lines are a good velocity reference for confirming the large blue shifts of the let's say the broad carbon-4 emission here, which is 2,240 kilometers per second. And the broad O3 is also very blue shifted relative to the halo frame. Generally, narrow features in quasar spectra are good indicators of systemic redshift, and they can accurately reveal large blue shifts in the broad emission lines. This is particularly helpful when the blue shifts are large across many rest UV and optical lines, such as O3. Overall, the measured properties of this line-emitting halo transition near 20 to 30 kbc from the center. The inner halo appears circularly symmetric, is kinematically coherent, shows blue-shifted Lyman alpha absorption and presence of carbon-4. The outer halo appears filamentary, shows kinematic shear, and has no blue-shifted absorption feature. A picture of a two-component circumgalactic medium is emerging from the literature. The inner region is dominated by moderate speed outflow driven in the past, and the outer region is dominated by inflow. In contrast to blue quasar observations, we have access to the innermost halo, and in contrast to inactive galaxy observations, we have access to the outer halo. So our results strengthen the two-component circumgalactic medium picture. The Lyman alpha halo is kinematically quiet down to the spatial resolution 6 kpc from the quasar, and this is in spite of the extremely fast galactic scale outflows traced by O3. In Lyman alpha halos surrounding radial quiet quasars, at present, no selection criteria on any extreme quasar properties have ever systematically found evidence of mechanical quasar feedback. Although fast Lyman alpha halo gas is occasionally detected around single blue quasars, the selection criteria for those quasars do not routinely find fast Lyman alpha halo gas. The fly still likes me. We compare ELQs with other quasars at similar redshifts and luminosities. Here I used the Reddest ELQ in a sample to illustrate, and the comparisons generally apply to the whole sample. For the Reddest ELQ J666 halo, Lyman alpha halo, the linear size is 140 kpc. The line luminosity is 5 times 10 to the 43 ergs per second, and the spatially integrated velocity dispersion is 304 kilometers per second. These values are within the wide and diverse ranges spanned by Lyman alpha halos around blue quasars, except for an only moderately suppressed Lyman alpha halo luminosity given the high bolometric luminosity. These comparisons suggest that the Quasar illumination pattern and the circumgalactic medium properties of ELQs are broadly similar to blue quasars. This figure on the left is showing circularly averaged Lyman alpha surface brightness radial profiles of the Reddest ELQ and various literature samples and single sources. The symbols at the top mark the exponential scale lengths of fitting exponential functions to these profiles. The ELQ Lyman alpha halo has a higher concentration compared to blue quasars. The figure on the right shows the flux-weighted eccentricities of the Reddest ELQ and literature sources. The sample medians are plotted with larger symbols. The ELQ Lyman alpha halo has a more circularly symmetric appearance in the inner region compared to blue quasars. These features, higher surface brightness concentration and more symmetric inner halo, they are consistent with ELQs being in an earlier evolutionary stage than blue quasars. The idea is that past Lyman alpha emitting outflow materials have not expanded to the outer regions. The inner halo is then loaded with Lyman alpha emitting gas, and this gas of outflow origin lacks the asymmetric morphology characteristic of inflowing streams. So ELQs are consistent with being in a young transition phase in the standard evolution paradigm. This picture is also discussed in other papers about obscuration at different wavelength regimes. And here about the illumination. The figure on the left shows the carbon-4 to Lyman alpha ratio and helium-2 to Lyman alpha ratio in the inner halos of the Reddest ELQ and literature sources. The ELQ's inner halo helium-2 to Lyman alpha ratio is as low as other type 1 quasars, which is lower than type 2 quasars. And then the figure on the right shows unweighted eccentricities of the Reddest ELQ and literature sources. The sample medians of the literature samples are plotted with larger symbols. The ELQ overall halo morphology is as asymmetric as other type 1 quasars, which is less asymmetric than type 2 quasars. These are higher. So the measured halo properties of ELQs are dissimilar to type 2 quasars of the unification model. And this suggests ELQs have unique physical conditions that are beyond orientation differences from other known quasar populations. So I said that the ELQ Lyman alpha halo luminosity is only moderately suppressed, but this should not be interpreted as obscuration cannot be global. And this is because halo emissions are not predominantly ionization bounded. One possible obscuration geometry is that of the Glickman 2022 picture. So this may be too simplified, so it's just illustrating. As a viewing angle, broad emission lines are visible. So it's a type 1. The quasar is not reddened by the torus, but it's by being embedded in a global and patchy dust distribution. Here's a summary. Quasar reddening allows views of the innermost halo. The Lyman alpha spike commonly observed in ELQ spectra is inner halo emission. In general, narrow emission lines are good measures of the systemic redshift, and they can confirm the large blue shifts in the broad emission lines relative to the halo frame. Our ELQ observations support the picture that the inner circumgalactic halo is dominated by moderate speed outflows driven in the past, and the outer halo is dominated by inflow. ELQs have higher halo concentration and more symmetric inner halo morphology compared to blue quasars. These are consistent with dusty quasars being earlier in evolution. ELQ's inner halo helium-2 to Lyman alpha ratio and overall halo asymmetry are dissimilar to type 2 quasars. These suggest unique physical conditions beyond orientation differences from other known quasar populations. We find no evidence of mechanical quasar feedback in the Lyman alpha emitting halo gas, and this is despite the powerful galactic scale outflows. During this work, I compiled a lot of literature measurements data and of other quasars, and you may ask me for them. Our ongoing efforts on the ELQs are these. Yeah, we are studying the spatially resolved ionized outflows observed with CAC OSIRIS plus adaptive optics and JWST near spec, the molecular gas observed with ORMA, the stellar gas and dust components observed with JWST's near spec and MIRI. Finally, I suggest 3 future lines of directions. First is to search for even fainter redder quasars following up on their extended emissions and compare with the first quasars. I think ELQs are analogs of the first quasars. They are young and globally dusty, possibly on galactic scale, resulting in a characteristic spectral energy distribution. Second is to search for signatures of quasar feedback on circumgalactic scales other than fast flows, especially at later cosmic times. My third suggestion is to search for quasar-driven outflows in line absorption, which is more sensitive to underdense gas. Thank you for your attention.
Thank you, Marie. Questions?
Thank you for the talk. I'm curious, how many of these extremely red things have some sort of imaging from whatever sources you have in terms of optical or near infrared? And are they typically unusual galaxies in the sense of ellipticity, shape, or size?
Thank you for your question. So we are selecting redshifts 2 to 4 extremely red quasars. So even though we call them extremely red, we are talking about a slope from rest UV to mid-infrared, but they are not that faint in the rest UV. So it's really difficult to measure the host galaxy. We tried, but we need JWST, and we are getting data.
Thank you for your talk. I'm just trying to I apologize if you alluded to this at some point, but I know there's been claims about an excess of BALs in the ERQ or highly reddened populations. Can you comment on how your sample does or doesn't overlap with that population?
Yeah, so for BAL, so we do find that even just in the Bose quality spectra, we are seeing that compared to blue quasars, the ELQs have more BAL fraction. And then with the highly reddened quasar population, so there are many different color and brightness criteria for selecting dusty quasar populations. And some people select by optical, some by infrared colors, and it's a very ununiform selection. So I think comparing ELQs with other dusty quasar populations, the most notable thing is that they have the fastest O3. So I think it's a more uniform selection, and you're really catching that transition phase between dusty starbursts and blue quasars instead of mixing in things from different stages.
Another question?
Can you give me a rough estimate of how rare are these ERQs in terms of the numbers you get compared to the full population? And if not too rare, is it possible that you can find some counterparts at lower redshifts that might serve as, just another source of information for this type of object?
Yeah, so with the ELQ definition, if you just follow the definition, then they are 2% of the Bose quasars. So if you're interested in lower redshift red quasars, I would suggest the F2M population. F is first, and then M is 2M is 2 mass. So I'm looking at. Yeah, this person, Glickman 2022, they are selecting at lower redshifts, and yes, you can see the host.
All right, let's thank Marie again.